When you type a question into an AI and an answer just appears in seconds, it really does feel like magic. But what is actually going on behind the curtain? Well, today, we're going to follow the high-speed and frankly high-stakes journey of a single prompt to see exactly how these incredible systems pull it off. We get these answers almost instantly, right? So we hardly ever stop to think about the raw power and, well, the infrastructure it takes to make it all happen. This isn't just about some clever code. It's about a massive, ongoing operational cost. So let's get real. How expensive is this magic anyway? Some estimates put the cost of running a service like ChatGPT at upwards of $700,000 every single day. Yeah, at that kind of scale, efficiency isn't just a nice-to-have. It's the only way to stay in the game. Every millisecond, every single byte of memory saved, it all matters. A lot. Okay, so where does our prompts journey even begin? Before an AI can't even think about giving you an answer, our words have to be translated from, human into something a machine can actually understand and work with. This first step is called tokenization. It's a fancy word, but all it means is the model breaks down our words into a series of numerical IDs, or tokens. So a simple phrase like, "Hi, my name is," gets turned into a sequence of numbers. From this point on, the AI isn't seeing words anymore, it's only seeing these numbers. Now, once it's turned into numbers, our prompt doesn't just get to jump to the front of the line. Oh no, it goes into a waiting queue, basically lining up with thousands of other requests from all over the world. They're all just waiting for their turn to be processed by the AI's core, the inference engine. All right, now we get to the absolute heart of how all of this works so fast. To really get how AIs generate text so quickly, we have to understand their short-term memory. And it has a very specific, very important name, the KV cache. Okay, so here's the crucial part. As the AI reads your prompt, it's doing all these incredibly complex calculations, and it stores the results as keys and values. The key value cache, or KV cache, is simply the place it saves all that hard work. And why does it do that? So it doesn't have to recalculate everything from scratch for every single new word it generates. It's a massive, massive shortcut. This whole caching thing happens in two really distinct stages. Think of it like a two-act play. First, you have the pre-fill. This is where the engine just blitzes through your entire prompt all at once. Its main goal? Build that initial KV cache. Then, once that's done, it switches to Act 2, the decode stage. This is where it generates the response one word at a time, constantly reusing and adding to the cache it just built. So you can probably guess that storing all these KV caches for thousands of people at the same time creates a massive memory headache. To solve it, engineers developed this absolutely ingenious system inspired by how modern computers work. It's called paged attention. All of this action takes place inside the GPU's video RAM, or VRAM. The best way to think about VRAM is like a small, extremely valuable plot of land in the middle of a city. Everything the AI needs to think, to remember, to respond, it all has to fit inside this one limited space. It is the most precious resource in the entire system, period. And what's on this prime piece of real estate? Well, you've got the model weights, that's kind of like the AI's permanent brain. You have activations, that's the temporary scratch pad for calculations. But look at what takes up the most room by a long shot, the KV cache. That's the short-term memory for every single person using the AI right now. Managing this space is absolutely critical. So here's the brilliant solution. Instead of letting every user's KV cache take up some random, messy amount of memory, the system divides the entire memory space into thousands of little, standardized, fixed-size chunks called blocks. It's like taking that huge plot of land and organizing it into perfectly identical lots. So how on earth does the system keep track of which prompt is using which block? It uses something called a page table, which is basically a master ledger or like a city planner's map. Now, this table doesn't store the actual data. It just points to which blocks belong to which prompt. It's the key to managing all this memory with like surgical precision. Now, all this clever memory management, it has an ultimate payoff. Because the memory is organized so neatly, the engine can do something called continuous batching, and this is a true game changer for performance. Let me walk you through how it works. So, imagine prompt A comes in and boom, it gets assigned a memory block number 12. Then prompt B arrives, it gets block 45. Now, the second prompt A is done generating its response, what happens to its block? It is instantly marked as free, and a new prompt, prompt C, that's been waiting in the queue, can immediately be assigned to that very same block.
And that's the whole principle right there. Zero wasted time. The moment a resource is freed up, it is put right back to work. No memory just sits around doing nothing, which means those super expensive GPUs are always working at maximum capacity.
And this is the result. The older methods, called static batching, were so inefficient, they had to wait for a whole group of prompts to finish, leaving these huge gaps of wasted memory and idle time. But with continuous batching, look at that! Memory waste is almost completely gone, which leads to huge gains in how many people can use this system at once.
So what does this all mean for the future? This whole complicated, hidden journey that our prompt takes, it actually reveals the secret sauce to making AI work for millions, and soon, billions of people. See, it's not just about building bigger AI models, it's about smarter engineering. Innovations like page detention are the unsung heroes that make it financially possible to give these incredibly powerful tools to everyone. Without this kind of smart thinking, the costs would be, well, they'd be astronomical.
And this leaves us with a really fascinating question to think about. As these AI models continue to grow at a crazy pace, the memory and cost challenges are only going to get bigger. The system we just looked at was a brilliant leap forward for today's AI. But what's the next one? What's the next big idea that will keep this amazing technology affordable and accessible for all of us?